So we're going to be working on the last part of this section. This is the last page of 9.4. And we need to add in a new thing here. If we have, where are we at here? We did all this. There we go. Sorry. So when we have two vectors, u and v, and we want to find the dot product. So dot product is you take the x values and multiply them, you take the y values and multiply them, and then add them together. So when we use the dot product to find the angle between two vectors. So here's our formula. Write it down. You're going to use it a few times. Determine the measure of the angle between these two. So what I'm going to do is I'm going to plug in cosine of theta equals the dot product of the two gives me 3 times 1 plus 0 times 4 all over the magnitude of each of them. So the magnitude of 3, 0 would be square root of 3 squared plus 0 squared, which gives me 3. So I'm going to put 3 there. And I'm going to multiply that by the magnitude of the square root of 1 squared plus 4 squared, which gives me the square root of 17. And so when I get that on my calculator, I'm going to take the inverse cosine of each side to get theta by itself. And I get 3 over 3 times root 17 inverse cosine of that. And I get 76 degrees. So the angle between those two vectors would be 76 degrees. Determine the measure of the angle between these two vectors. Well, same dealio, just the second one. Let me give myself some room here. So I'm going to take the dot product for the top. So I'm going to do 15 times negative 4 plus negative 3 times negative 20. And I get negative 60 plus 60. Well, I can see already that I get a 0 on top. And let's get the magnitude of each one of them. So I get the square root of 225 plus 9, 234 times 416, and I don't really care if you simplify those because you're just plugging them into a formula. So if I take the inverse cosine of 0 over anything, the inverse cosine of 0 gives me an angle of 90 degrees. So we know that those are called orthogonal. It's another vocab word. When two vectors are perpendicular, we call them orthogonal. All right, so let's get a good start on 9.5 here. Parametric equations. Given a particular relationship among two variables, say x and y, introduce a new parameter, say t, that varies with both of the variables simultaneously. So the equation y equals 1/2 x can be represented as a system of parametric equations. So the x is the same as 2t and the y is t plus 1. So most equations can be turned into parametric equations by using the process here. The benefit of a parametric equation is that you can see the direction of the motion. For instance, if we do a parabola shape, you'll be able to see it, that your graph is moving in a certain direction. And that kind of tells you the motion of what's going on, which is kind of important for some of this stuff. Consider the set of parametric equations. X is equal to 2 cosine t and y is 5 sine t. Make a sketch of the curve using multiples of pi over 2. Give the direction. So I'm going to take my x, y, and t values, just like we did before. we're going to do 0, pi over 2, pi, 3 pi over 2, and hopefully 2 pi is going to give us the same thing, so I won't do that. So let's plug in here and see what happens when we plug in these values. So if I plug in 0, the cosine of 0 is 1, so I get a 2 times 1 is 0. The sine at 0 is 0, so I get a 0. And then if I do the same thing at pi over 2, the cosine is the x value at pi over 2, so I get a 0. The y value at pi over 2 is 1, so I get 5. Oops. Yeah, well, I'll make sure I get them in the same row here. At pi, I'm going to get negative 2, 0. And at 3 pi over 2, I get 0, negative 5. So the moral of the story here is when I graph this, I get a starting point at 2, 0. I know where that value starts. And at pi over 2, 1, 2, 3, 4, 5, I'm there. I know that it started here and the motion went that way. Notice that I put the arrows in there so you can see which direction things are moving. And then it moves back, of course, it'll move back there, and the motion is that way. So you can see the motion of it as it moves using finding these values from 0 to 2 pi for t. Now, let's do a little bit of messing around here with this. We know that we have the equation x equals 2 cosine t and y equals 5 sine t. If I divide by 2 here, I get x over 2 equals the cosine of t, and y divided by 5 equals the sine of t. And if we use this Pythagorean identity that we've used in the past, sine squared theta plus cosine squared theta equals 1, and we plug these guys in, I get a y over 5 squared plus x over 2 squared equals 1, which gives me y squared over 25 plus x squared over 4 equals 1. And if you recognize that as being the rectangular coordinate equation for an ellipse, it kind of follows that the parametric graph and the rectangular coordinate graph should be very similar. So parametric equations, traces counterclockwise, traces clockwise. You can see some of those. There's your ellipse. I'm sure in Algebra 2 you talked about ellipses quite significantly. So let's take a look at this. A football is kicked and its position at time t is given by a set of parametric equations. So we have that where x and y are both measured in feet. Sketch a graph of the parametric equation. Well, if you have a TI calculator, or you can get to a calculator that does parametric equations, if you go on the TI 84 or 83, if you go down to right below where it says radians and degrees and go over to PAR, you can put in parametric equations. So when you go to y equals, you get a x sub 1, y sub 1. So I'm going to put those in. I'm going to pause. So I'm going to tell you my window so you kind of see the same thing I see. When it talks about T min and T max, I have a T equals 0 to probably, I think 5 is enough. Because if this is a ball being kicked, it's going to be less than 5 seconds for it to come back down. And then for my T step, I have 0.2. That means your calculator is going to be figuring out what's going on every 2 seconds. I have an x min of 0 and an x max of 200. If they kick it more than 200 feet, that's pretty great. And I have a scale of 50, because I don't want to have too many tick marks across the bottom. On my y min, I put 0 y max. I put 50. If the ball goes more than 50 feet high, I'm impressed. And scale, again, I went with 10, so I wouldn't have a whole bunch of tick marks. So if you do all that, your graph is going to look a lot like mine. So when I graph it, I get a graph that looks something like, a parabola, which I would suspect when we kick a ball that it's going to be parabolic shape. So how far down the field is the ball in 2 seconds? So if I go to my table and I put in 2 seconds, or ask it to do 2 seconds, or if you have depending if you have it on ask or if it goes on, if it's automatic, you can do either one. So at 2 seconds, I get that the ball is 138.6 feet down the road, and how high is the ball at 2 seconds? The y value is 16 feet, so it's still in the air at 2 seconds, but it's definitely coming back down. How long is the ball in flight before landing? Well, we know that exactly 2.5 seconds, the height of this is 0, so when the y value is equal to 0, it's back down on the ground. So I'm going to go at 2.5 seconds. How far does the ball travel before landing? Well, that's kind of a good question, because horizontally it moves 173.25 feet. That's the horizontal movement, but we know that the ball had to do some up and some down in that distance, and that's not what the question is asking. It's asking for the horizontal movement. So if we eliminate the parameter, write the function in x and y. So when we do that, we have to solve one of them, and let me move this. Solve one of them for t and move it into the other one. So if I solve this first one for t, I get x divided by 69.3 equals t. And then I can plug that into the other equation, so I get y equals 40 times x over 69.3 minus 16 times 69.3 over, or x, oh darn it, x over 69.3 squared. And so there's your equation in just x and y, and you can spend some time simplifying it if you want to. I'm running out of time here. So when does the ball reach its maximum height? Well, since it's a parabola, we can always use negative b over 2a. So if I use the equation x equals negative b over 2a, from this equation up here, we know that our negative b would be negative 40 over 69.3 over 2 times negative 16 over 69.3 squared. And so the maximum height, I already plugged this in so I could get an answer, and I got a x value which corresponds to a y value of 25. So it got 25 feet high. And I was just using the negative b over 2a. Let's stop here.